Hello everybody, thank you for attending RSA webinar today. My name is Artur Kosakowski and I will be running today's presentation together with my colleague Rafał Gawenda. The topic of this webinar is vibration of floors and footfall analysis. Because of the complexity of the covered topics, I'd like to start with the description of the theoretical background of floor vibrations and footfall analysis, and then show the implementation of these analyses in robot. The webinar will be the combination of slide presentation and live use of robot, followed by Q&A session. As the microphones of attendees are muted, please submit your question using the question box of the GoToWebinar panel. In this webinar, we will focus on basic assumptions of dynamic analysis of structures, parameters of model analysis, dynamics mass definition, forced harmonic analysis in the frequency domain FRF, and influence of damping, footfall analysis and the results available for this type of analysis. At the end, we'll look at the frequently made mistakes in definitions of model, harmonic FRF, and footfall analysis, as well as tips and tricks. On this slide, you can see the basic equation of motion. It is its general form for forced vibrations containing mass, damping, and stiffness matrix. When defining any dynamic analysis in robot, mass matrix is constant and it doesn't change during the analysis. The same applies to the stiffness matrix for all types of analysis, including FRF and footfall, which we discussed today, except of static nonlinear analysis and nonlinear time history analysis. In dynamic model analysis, this equation simplifies to the form shown on this slide. This equation defines the eigenvalue problem, and solving it enables to calculate natural frequencies, also known as eigenfrequencies, and associate shapes of vibrations called modes or eigenvectors. The mass matrix M is the equation in this equation corresponds in robot to self-weight, added masses, and load to mass conversion. Let's look at the example of a flat slab supported by linear supports at its outer edges and some nodal supports standing for columns. I will now switch to robot, and first I will define, as you can see, there are several static load cases already defined with corresponding loads, but I will start with definition of the model analysis. I will decide on 20 modes, and I will calculate the model. The model analysis, as you already know from the previous webinar, especially on seismic design, is the first thing when you start dynamic in robot. So let's have a look at the results that we have for this kind of analysis. We may go to, I will select the model case. I will go to results and diagrams. I will select the first shape of vibration, and when I activate the formation, I can clearly see the shape of vibrations. Okay, we can now switch between the modes to see different shapes, and on the screen you can see the corresponding eigenfrequency. The same can be seen as a text in the model analysis table. Okay, so we have frequency and we have masses that correspond to a particular shape of vibration. Well, I mentioned that by default, mass in the mass matrix we have a self-weight of the structure for model analysis, but also when we have model analysis, it is possible to define both nodal or bar, uniformly distributed masses. Of course, as the masses usually correspond to applied loads, we have the option to convert the defined load into into the masses. So I will convert case 2 into mass with coefficient 1. So all the load is going to be treated as a mass. And for case 3, I will convert only 30%. Okay. So now, if we calculate the model, we can see the change in the frequency. The frequency is now lower than it used to be before. So right, let me go back to the presentation. A harmonic analysis in the frequency domain, FRF, corresponds to force vibration of specific type. It treats all loads defined in the associated load case as amplitudes of harmonic force from some range of frequencies. The obtained results, such as displacement, acceleration, forces, moments, are also amplitudes corresponding to steady-state sinusoidal harmonic vibrations. In case of a model with many dynamic degrees of freedom and with non-zero damping, the typical diagram of response in the function of frequency may look as the one on the picture you can see on the currently displayed slide. For FRF analysis, we define loads which change in sinusoidal way, and robot checks the response of a structure for a certain range of frequencies. The typical results are shown on the displayed picture. As you can see, it is a similar diagram to the one from the previous slide. Let me go back to my robot model, to my slab, and we'll try to define FRF analysis. So I will press the New button, and now I can select FRF analysis. I will set the range of frequencies between 5 and 15 Hertz. I will leave this checkbox marked, but I change the damping to 1%. Okay, and now I need to define the load. So I will select nodal force of magnitude equal to 0.7 kilonewtons, 70 kilograms. That's the human weight. And I will apply that in the node of a slab. Well, let me calculate the model. Okay. As you can see, this is one of these complex load cases when you have several components, and therefore you have plus and minus envelope created, filters created for displaying results in the table, similar for example, code combinations. And you can access these components here, and when you change the components, you can see different results, different vibration shapes. Okay, we may go to the diagrams and we may normalize that. Okay, so we can see the results for each of the component. These results are also available in the tables. Let me go to the results, and then we go to advanced, and then we have the tables for FRF. So let's have a look at the diagrams. And for example, we may see the displacement of the node where we applied the force. Okay, vertical displacement. Okay. And we open that in a new window. Okay. Well, as you can see, because the number of divisions was small, the diagrams is not smooth. But what I'm going to do at the moment, I'm going to make two changes. First of all, I'm going to change the units of displacement, the precision of the display of the displacement, so that you can see the values. And in addition, in the tape column, I'm going to add the information about maximum and minimum value that we obtained. Okay, so now if I go to the parameters of FRF analysis, I can change this number of divisions to larger, for example, 200. And if I recalculate the model, the diagram should look much nicer. Yeah, you can see it's much smoother now. And I may add the diagram of another point, for example, node 1.154. Okay, that's a vertical displacement as well. Okay, change the color. For example, this one, and we can see. Now you can see that you can identify symmetric and antisymmetric modes for looking at the displacement of these nodes, which are actually defined on the opposite sides of this slab. So we have, okay, let me type 154. You can see that one node is here and one node is over there. We can also add the information about acceleration. So, okay, vertical acceleration in node 132 and 154. And I will move them to the diagram. As you can see, the magnitude is much larger than the displacements. So I will remove the displacements from the diagram. Sorry, I removed the displacement. I need to have both accelerations. Yep. Okay, like that. And also I will go to units and we'll change the displacement to meters so that we have the information about the acceleration in meters per second squared. Okay, so you can see also the maximum and minimum value in the table. Okay, let me go back to the slides. We can also see the strong influence of damping on the reduction of resonance peaks. So if I go back to my model again, okay, now I will go to the parameters of FRF analysis and I will change the damping from 1% to 3%. Okay, and I will calculate the structure again. You can see that the acceleration is much smaller, and also if I have a look at the displacements, they are also lower. I will go again to units and I will change the units to millimeters. Okay, yep. So that was, if I remember correctly, 0.24 millimeter. Now we have half of that value. So you can see how damping, to which degree it influences the obtained results. Okay, let me go back to the presentation. Now let's focus on the FOOTFALL analysis. This analysis is a code-based one, therefore I'd like to start with some references which were used for the implementation of this functionality in robot. You can see them on the currently displayed slide. FOOTFALL analysis is to some extent similar to harmonic FRF analysis. It is also based on harmonic sinusoidal force input, but in case of FOOTFALL analysis, single harmonic components are not used. To model the FOOTFALL effect in a way closer to reality, the more complicated continuous function used, and this function, as it is stated in the code, can be broken down into a series of sine waves, each of which has a frequency at an integer multiply or harmonic of the forcing frequency. Each harmonic will have an associated amplitude and phase shift, and the set of harmonics are known as a Fourier series. One may sort of say that footsteps are composed from several harmonics with increased frequencies. In general, the first harmonic with the lowest frequency corresponds to the frequency of footsteps, with ranges being defined in given code as shown on the currently displayed slide. Similar approach is used for stairs. On the top part of this slide, we can see the diagram showing harmonics of Fourier series for low-impact aerobics with 4 harmonics plus a static force corresponding to the weight of a person and the total force value. As it is more for damping, there are parts with large values when a person lands on the floor and zero-value parts when he or she is in the air. The table below corresponds to the walking activity on floors, and it is also approximated by 4 harmonics. In case of SCI P354, these are amplitudes FH at frequencies and phase angles. Alpha H is often called dynamic load factor, DLF, and for each harmonic, it is the amplitude of dynamic force expressed as a fraction of a person's static weight. When you add up all harmonics together, the minimum value would be around 0.6 rather than close to 0, as for the aerobic diagram. Also, the maximal values would be smaller comparing to the ones for the aerobic activity. The response of a structure to footfall depends both on the frequency of force function, footfall, and the eigenfrequencies of the floor as well as damping. There are 2 types of responses, resonant and impulsive. The resonant response is similar to harmonic FRF analysis, and the impulsive one is the one where each of footstep is sort of a separate action and is calculated with the use of time history analysis. The prior type is usually dominating from low-frequency floors, whereas the latter for the high-frequency ones. As you can see, code sets the limit value in different ways, and it is worth noting that different responses may dominate in different parts of the same floor. One of the ways to describe the variable response, like the variable acceleration, is a peak value. However, the peak value does not describe the amount of time the system is subjected to this level of response. Therefore, we often use root mean square or RMS value instead. In case of acceleration, this value is defined by the first formula from this slide. In case of sinusoidal signal, the RMS value is square root times less than the peak value. Another way of presenting the variable response, which gives more emphasis to higher values, is the root mean quad, or RMQ. This value is calculated according to the bottom formula shown on this slide. Another topic related to footfall analysis are the acceptance criteria for human comfort. Human perception of vibrations depends on their frequency. This diagram shows the base curve for human perception of continuous vertical vibration according to BS 6472 code based on RMS acceleration and the logarithmic scale. In the most sensitive frequency range between 4 and 8 Hz, the criterion is constant acceleration. Above 8 Hz, it is linearly increasing acceleration, which corresponds to constant velocity. The basic value calculated by footfall analysis for SCI P354 and for concrete center provisions is the response factor, R. It is a multiplier for the level of vibration compared to the average threshold of human perception. The response factor of 1 corresponds to the magnitude of vibration just perceptible by human, while R equal to 2 corresponds to the vibration twice stronger. R equal 4 corresponds to the vibration 4 times stronger than perceptible by us, and so on. In case of the resonant response, R is calculated for each harmonic and then combined as square root of the sum of squares combination. In case of impulsive transient response, R is based on RMS values calculated from time histories using 1 second averaging period. Let's have a look at the values of response factor used in practice. For continuous vibrations in floors, usually the response factor equal to 4 or to 8 is adopted, but it may be smaller for residential buildings, hospitals, and other buildings with similar purposes, as you can see in the example from SCI P354 based on British Standard 6472. In ISC DG11, the response factor quantity is not used, as the acceptance criteria is based directly on the ratio between the peak acceleration and the gravity acceleration, as visible in the last column on the right table. Let me show some recommendations related to footfall analysis. It is suggested to set the dynamic value of the modulus of elasticity for the concrete as 38 gigapascals for normal weight concrete and 22 gigapascal for lightweight concrete, rather than the typical Young modulus values, which are different for different concrete grades. For load to mass conversion, it is recommended to use 1.0 coefficient for self-weight and other dead loads, and 0.1 for live loads. Let's get familiar with the footfall analysis parameters. In the top right corner, you can select the code on which you want to run the analysis. In addition, you can select the excitation method. Contrary to FRF, where you define excitation manually for footfall, this is done automatically. For the self-excitation, the excitation is defined in selected nodes only, and the response is calculated for the same group of nodes. In other words, you can't see the results for nodes in which there was no excitation defined. This is possible for full excitation, but the analysis will take longer comparing to the previous method. As already mentioned, the recommended walker weight is 70 kilos, and the suggested damping value were presented on the previous slide. Mind that the model analysis for footfall by default includes only the vertical direction. The frequency limit is usually defined by the code. So let me go back again to robot, and I will close the, we'll switch to the view, the structure. Okay, I will close these dialogues now. Okay, I will define a new load case, footfall analysis. What I'm going to do, I'm going to select the code, SCIP, self-excitation, and I will select the damping as being 3%, and I will go to model analysis parameters and I will set frequency limit as 15 Hz. Okay, so I will calculate the model now. It's going to take a bit because I still have FRF analysis defined in this example. Okay, done. So let's select the FOOTFALL case that we defined. We can go to the results, and in advanced results we have a group of results that corresponds to FOOTFALL analysis. So let's have a look at maps first. So we may see these two response factors, transient and resonant. And when you display the overall, that's going to be a higher value of the two, resonant and transient. So this is like a superposition of the results. If I display velocities, for example, you can see that there are no results because the code that we selected, SCIP, simply doesn't require these results to be calculated. So depending on the selection of the code, certain group of results may simply not be available. But we may see, for example, overall acceleration. Okay, let's go to another results in a different presentation. In the results, we have also FOOTFALL analysis tables. And you can see values in each of the node. You can see that, as I mentioned, the node in which you check the results corresponds to the excitation node. So that's basically the results are for the node in which we have the excitation, because we selected this self-excitation method. Okay, we can go to table columns and we may select or unchecked certain columns. And of course, we have also the table. The table includes at the moment supported nodes, so we can go to the selection and we may use the selection dialog to just remove all the supported nodes that results in the supports are not interesting. Okay, we can go to the extremes tab and we can see where we have the highest overall acceleration. That's, for example, in our case, that's node 133. So now if we go to the results in the graphical form, advanced, and we have FOOTFALL analysis diagrams, we may display the results for this very node, 133, 30, and the excitation. Okay, so you can see that we have the diagrams showing the influence of each harmonics, and if you look at the total overall value, that you can clearly see that the fourth harmonic corresponds the most. If I change the excitation node, for example, to node number 2, you can see the change in the diagram. Okay, let me return to excitation node being the same node as we display the results for. And then, okay, let me go back to robot let me go back to the parameters to load to mass conversion. Okay, you remembered that at one of the previous slides, the Eurocode value for live load conversion is 0.3, but this is considered as being conservative value. So we may see if there is any influence if I modify that load to mass conversion using smaller coefficient, and now I can recalculate the model and see whether that changes the results and how much. Yeah, you can see there is a change in the diagram after this modification. Okay, so let me go back to my slides. And let's focus. Let me focus your attention to the most common mistakes for dynamic analysis. If we have a look at the self-weight, and I will go back to robot again. If we go to the loads table, we can see that in this example, the first load case is a self-weight, right? And if we want to convert the self-weight into mass, okay, with coefficient 1, we should do the following. We should make sure that in model analysis we mark disregard density to avoid the situation that the self-weight is duplicated for calculations. That's the first step. And also, if we have footfall, we should do the same in the parameters of model analysis for footfall. And also mind that in the footfall, only Z direction for mass is active. So if we want to compare the results between footfall and model analysis, you should make the corresponding change in your model analysis as well. Okay. So this is what this slide says about being careful about load to mass conversion for self-weight. Okay. That's right. Sorry. Okay. The default maximum frequency limit is set usually as 15 Hertz. Is set as 15 Hertz in footfall analysis, and due to this fact, you may have no results if the eigenfrequency of the structure. I'm sorry, it seems that you probably can't see this slide. Okay, let me. Okay. Yeah, I think that's the correct slide. Okay, it may happen that there are no results for footfall analysis as the eigenfrequencies of the structure is higher than the specified limit, which is by default 15 Hertz. Also mind that for selected code, some types of results are not available, as you could see, as you could have seen for my slab model. That was for velocity. In case you need to see the response in different location than the excitation happens, you have to use the full excitation method. But as I mentioned, the full excitation requires more time to complete calculations, than self-excitation method, so use it only when you really need to have these results. Mind that the footstep excitation forces are applied independently on each of the nodes, and there is no interaction between them, even when full excitation is activated. This is how the code requires this analysis to be performed. In case you have different types of excitations than a typical walking, you should use the time history analysis instead. Finally, I'd like to encourage you again to use these links to learn more or find solutions for your problems. And that's the final slide of my presentation. Please feel free to ask questions now.
Thank you, Arthur, for the presentation. So if you have any questions, please fill them in a question and answer panel in TeamViewer window. There are some questions about the providing links and publishing the presentation. As usual, the video will be published in our YouTube channel and it will be done within 1 or 2 days. And also, when we prepare a slideshow, it will be also available on our webinar thread in our forum, so everybody can access either presentation or video published. Arthur, can you explain the difference between full excitation and the self-excitation?
Okay, so that was, I think, covered in one of the slides. So let me try to go back. So you can see the basic difference is that for self-excitation you cannot see the results in nodes that are in which you haven't defined the excitation, whereas for full excitation you can. There's a question I can see about the addresses. I mean, like I assume that's for the link. You don't know. There's no need to note them. The presentation will be available for download, so you can click on that. So, but of course I can go back to. Let me see. Okay. So basically you can just use the Google search and type these keywords, and you should be able to. AKN stands for Autodesk Knowledge Network.
There is a question about covering or going back to cover how to make a robot model starting from, let's say, architectural to structural. So we encourage you to go to our forum and check the forum and find the right way to do so, because this webinar topic does not cover this subject.
And also, you may want to have a look at the previous webinars. If you are a Revit user, there was a webinar done by Rafał on a link between Revit and robot. So your architectural model actually is a Revit model. That's the webinar to watch. And if you look at the first webinars, there is also a lot of information how to make structures so that it can be correctly meshed, how to avoid errors, and also where to use column rather than very narrow vertical panel, or where to replace the what to do in case of the openings located very close to the slab edge. There is a lot of useful information. I think you may want to have a look at these webinars, and also, as Rafael said, you feel free to ask the question on robot. We or other robot users are very happy to help.
There is a question about the masses. Does it mean if all X, Y, Z model masses are active in model analysis, then the footfall analysis is wrong?
Well, my understanding of the footfall analysis is that your weight actually goes vertically downwards. So that's the reason. That's the reason you want to have only vertical direction for the mass active. So you do not expect to have any horizontal, let's say, movement of the slab. But this is simply footfall analysis is code based, so it is as defined by the code. Okay, it's 10%. Okay, so well, again, the code, according to my knowledge, gives you the requirement how to consider loads as a masses. So as it was presented on one of the slides, for Eurocode actually, it's okay, consider all dead loads as being masses and 30% of live loads. But if you look at some references, they often point that 30% of live load is excessive, and they recommend 10%. Of course, the reason is that there is a likelihood that if you increase mass, then it is more difficult to keep this response factor below the targeted limit. So you may end up with much heavier floor. But of course, that's going to be the structural designer decision whether 30 on 10% of live load.
Can we do the same analysis for the customized steel plate?
The model doesn't really matter. I mean, you can create any model and run footfall analysis. This is not linked to a particular type of the model. So you can, absolutely. So usually you separate a floor from the building, but okay, how the floor is constructed is, of course, how it is constructed. So you should model it exactly as it is.
It's about question about a certain percentage of the body weight to create horizontal force.
I can't answer that. I mean, I have never thought about that. That's not something that that is like referred to. I'm not sure. I mean, like it's rather difficult. I mean, okay, when you jump, you can see that the floor starts to move vertically, but in a typical building, I can hardly imagine the situation that you have as a person walking or running or doing this sort of activity are able to cause horizontal vibration. I mean, that's sort of like moving the entire building. I've never tried that actually, but I don't think that would cause any significant results. But if there is a recommendation for that, I mean, you may try to define such kind of analysis and see the outcome.
There is a question about considering 10% of superimposed loads, finishes and live loads in P354 code. But we are really not experts in this matter, so.
Yeah, but this is like simple load to mass conversion. So if you think, okay, the load that I defined should fully or partially participate in this analysis, you just make the load to mass conversion. I mean, this is what you can see here. So if you say that, okay, my case number 3 corresponds to superimposed load, or as actually is live load in this particular case, then you simply convert that with the 0.1 coefficient, and that's all. And you can see that, okay, if I click here, and you can see that actually the third load case is a live load, and it has been converted. Yeah, so analysis types, okay, that's a live load that was converted. So okay, so I think that sorry, so I would like to thank you all for attending this webinar and invite you to join the next one on time history analysis, which is scheduled on the 25th of May. Thank you again for attending this webinar.